I've changed these around a little bit. So these first set of notes that I have on here, they're not on your notes packet, but later on we'll have some stuff in our notes packet. Okay? All right. So Newton's second law in the linear world. So here's the linear or translational world. Okay. Was written out like this. Okay. Well, actually, I'll ask you guys, what's Newton's second law written out in the linear version of it? What's that? Yeah, that's right. The sum of the forces, okay, the sum of the forces equals the mass times acceleration, okay, yeah, so we're going to look at both of those versions. And so our example that I want to give you is like this. If you'll remember, what this means is this. If I've got a mass, okay, if I've got a mass m, and I'm going to apply a couple forces. Let's call that F2 to the right, F1 to the left. Okay. If I wanted to, solve certain quantities for that, the Newton's second law version of this would look like this. It would look like F2, which is pointing to the right, F2 minus F1 would equal the mass times acceleration of that object. Okay? And if we look specifically at its motion, if we started with an initial velocity of 0, it would start off as a dot, okay, and then it would increase in velocity, kind of like that, okay? In what direction would acceleration be for this particular example? What direction would this acceleration be? To the right, okay? Acceleration would be to the right, so we're still using our motion maps. That's supposed to be an A. Okay. All right. And so if I were to solve this equation for the acceleration, it would simply look like this. I would take F2, subtract F1, and divide that by the mass. Okay? So does that all look familiar? All stuff we've done before, right? Okay, so that's what Newton's second law looks like in the linear or translational world. Okay, so here's what it looks like in the rotational world. So when you are doing these problems, think of the linear analog of these. Okay, so the rotational version of this looks like this. It says the sum of the torques is equal to the inertia times the angular acceleration. Notice the equations look very similar. Okay? So if I had some rigid body, in this case I'm going to make it a disk that has some rotational inertia I, okay, and I have a particular torque that I'm going to pull it, that it's going to experience. Let's call this torque 1, and let's call this torque 2. Okay, I'm really bad about drawing my 2's on these. So the rotational version of that, in this example, would look like this. I'm going to take the second torque, okay, because it's counterclockwise, right? So it's going to be positive. I'm going to subtract the clockwise torque, and I'm going to set those equal to the rotational inertia times the angular acceleration. Okay? All right, so if I wanted to find the angular acceleration, I would do a similar thing as I did over here. I would just take the two torques, find their differences, right, and divide that by its inertia. All right, and in this case, you need to you need to be, you'll either be given the rotational inertias, in this case for a disk, right? For a disk, let's just use a disk as our example. Okay. That's mr squared over 2. Okay, and that's what we would plug into there. So you need to know the rotational inertias. Okay?
So you get like a sheet with all the common inertia things?
Yeah. Yeah, I'll get it for you. Actually, you have it in the packet I gave you. In the
okay.
Not the notes packet, but the
big one.
the copy out of the book. Okay? All right. Now, what I want you guys to look at specifically is this. Not only do we have this equation for the torques, okay? When you're solving your problems for this particular web assignment, remember, by definition, we also said that the torque, okay, this is what we were just talking about, is equal to the force. What symbol have we been using for the lever arm? L, script L, okay? So the force times the lever arm. So that's also another equation that we have for solving our torques. Okay, so realize that in some of your problems, that it's actually possible to set these equal to each other, where you've got your inertia times your angular acceleration is equal to the force times the lever arm. So use this fact to help you solve some of the problems. Okay, because by definition, this has got to be true. That's the definition of the torque, the force times the lever arm. Okay, and I just told you right now, this is the Newton's second law version for one torque. Okay, all right. What I want to do is I'll go over some sample problems. All right. So the first sample problem I want to go over here is oh, you know what? I just wanted to show you this real quickly. You don't need to write any of this down. This is just comparing the two. Okay. So the strategy for solving these problems is substituting torque for force, rotational inertia for mass, angular acceleration for acceleration, and you essentially have what I just talked about. You just, instead of solving for this equation, okay, we're just using this equation. Just think of them as being analogous. All right. You wouldn't have gotten this far in physics if you weren't able to solve that. So if you can solve that, we're just replacing that notion with that. Okay. All right. What I want to do is I want to go over this problem here. Okay. So this is actually in your notes packet. It should be on page. The bottom, yeah, it's on the bottom left-hand side of page 3. Okay, and we will call this a wheel, right? I thought in a previous version this was actually a disc. All right, so this is actually a wheel or a hoop. So here's what we got. We got a 1 kilogram wheel. It's experiencing a force of 0.45 newtons. It's got a radius of 25 centimeters, which is how many meters? How many meters is 25 centimeters? Okay, good. 0.25. Man, I really have to work on my 2's. 0.25 meters. Okay. All right, and we know the mass is 1 kilogram, according to the problem. Okay, this force is applied for 5 seconds, and it says after this time, what is the angular velocity of the wheel? All right, so we, essentially we can go to our, once again, we can just go to our torque equation. We said we're experiencing one torque here. And our equations, we just finished saying, are the moment of inertia times the angular acceleration. And also we know that the torque is also equal to the force times the lever arm. Okay. So in order to solve this problem, I probably need to solve for the angular acceleration. Okay. So if I solve this for the angular acceleration, I need to set these two equal to each other, just like I said earlier. So we set the moment times the angular acceleration, which equals the force times the lever arm. Okay. So my angular acceleration is going to equal the force times the lever arm divided by the moment of inertia for a wheel. Okay. So one of the things you'll need to know is that for a wheel, this moment of inertia is actually equal to just mr squared. So that's an easy one to remember. Okay. So I'll take that and I've got to plug it into there. So generally speaking, that's given to you as part of the question as well. Okay. What the inertia is for the particular object. So I plug my values in. I get F times my lever arm. Okay. Divided by m over my r squared. Okay, which is my radius squared. Okay. What's the relationship between L and R in this particular problem? Look really carefully. So if this is my, yeah, they're equal. See how that's my force? So if it's perpendicular to that, my lever arm is going to be that length, which is the same as my R. Okay, so I can replace, let me replace the L with R. So I got R there over mr squared. So that'll just give me what? What does that give me? Okay, F over mr. Okay, so I can just plug my values in. My force is given to me as 0.45 newtons. My M is given to me as 1 kilogram. I'm going to leave the units out because I'm running out of space here. My R is 0.25. Okay, I'm trying to do a better job with my 2's here. There we go. 0.25. And I get a value of 1.8. What are the units for angular acceleration? Radians per, good, per second squared. Okay, so does that answer my question of what the angular velocity is? No. So generally speaking, what do we do in our class to get from here to my angular velocity? Okay. Good. Let's go to our strategy. I know you guys can just go straight to the equation, but let's go to our strategy here. So our strategy means writing out the 5 variables, the 5 rotational kinematic variables. Theta, omega initial, omega, alpha, and the time. Okay. So we're looking for our initial angular velocity is what according to the problem? What's the initial angular velocity? Okay, it's going to be 0 radians per second. We're looking for the final angular velocity. What's my angular acceleration? Good, 1.8 radians per second squared. Okay, and the time? 5 seconds. So of my equations, which one should I use to solve for my unknown variable? Okay. By the first one, do you mean this one? Okay. Is that the first one that's listed on your sheet? Okay. All right. So we're essentially just plugging these values in. My angular velocity is going to equal 0 plus 1.8 radians per second squared, okay, times a time of 5 seconds. And that's going to give us a value of 9 radians per second. Okay. The second question is, through what angle does the wheel rotate during this 5-second period? So what am I solving for there? Which variable am I solving for there? For B, what variable am I solving for? Theta, right? I'm solving for theta. So theta is equal to theta initial plus omega t, or omega initial t, plus 1/2 alpha t squared. 1/2 alpha t squared. Okay. We assume we start off at no radians, so 0, plus my initial velocity is 0 times t, plus 1/2, that should be a plus there, 1/2 alpha, which is 1.8 radians per second squared, bless you, times the time of 5 seconds. I'm going to square that. And that gives me a value of, I think I have it here, 22.5 radians. Okay? All right. So most of your problems are going to be like that, where you're using some version of Newton's second law in the rotational direction. Okay. Now I think that's enough time. I want to just show you really quickly a sample problem. Hopefully, I can do this in less than 5 minutes. Okay. So next time we're going to be doing these with more complex systems. Today we're starting off with really easy systems. Next time we're going to have pulleys and masses on pulleys, going back to other things that we've talked about before. Okay, I bring up this sample problem because it comes up on not only in your book but also on the AP test. Okay, so here's what we have. So let's say that we've got a string on this. This is on your. I think it skipped something. This is on your notes packet as well, right? Okay. So if we look at, let's change this in color here to red. Okay, so let's say this is a string. So we cut this. So we cut the string. And this rod that has a hinge, okay, has a hinge in this right there, rotates downward, okay. Where would we, just going back to what we were doing before, where would we say its weight is directed if we were to draw a force diagram? Yeah, in the middle. Okay, so its weight in the middle right here, okay, that's the main force there. It would be equal to m times g, okay? And relative to the lever arm for that is going to be what value? If the whole thing is L, what will its lever arm be? Okay, yeah, so its lever arm, L, will be equal to 1/2 of big L, because remember we said the entire length of it would be L. Okay? It says calculate the initial acceleration of the end of the rod. All right, so this object's going to go like that. All right, so we go back to the same thing we've been doing before. We go to our sum of our forces equaling the mass times acceleration. Okay, which we actually will find that we're not going to need that, but we still need to write it down anyway. And also the sum of our torques. In this case now, it's not going to equal 0. It's got to equal I alpha. Okay, so the object is only rotating. Okay, so we need to make a note to ourselves. It is only rotating. Okay. Now, remember by definition, we said the torque is going to be the force times the force it experiences, F, times its lever arm. Okay. Do you guys remember what the rotational inertia is of a rod on one end? Remember we proved it in class? Good. 1/3 the mass times the length squared, okay, times alpha. All right. So this force here, I only have one force. What's the force that this object is experiencing? Okay. This weight. Well, actually, there's a force from the hinge, but we'll make that the axis of rotation. So that's this F actually becomes mg. And my lever arm is how much? Okay. 1/2 L. Okay, so that becomes that part. And we got that equaling 1/2. Oops. I was looking at one thing and doing something else. Okay, so we got 1/2. Oh yeah, you're right, 1/3. ml squared alpha. So what happens in our equation here? Okay, the L's cancel? One of the L's. This L cancels here, right? That L cancels with that L. Anything else? The M's cancel. Okay. So we actually get the alpha as equaling 3g over 2L. Okay, that's the angular acceleration. Okay. Now, if we wanted, now notice it said calculate the initial acceleration. So that's the angular acceleration. Let's also find the tangential acceleration. What's the bridge for accelerations? Okay, so let's also find the initial tangential acceleration. Well, what's the bridge for that? You guys have that written down? Okay, good. Remember that the general equation for it is the tangential acceleration is equal to alpha times the distance times the radius r. Okay. Remember, do you guys have that down on your sheet as your bridge? Okay. It connects the rotational world with the angular, or the rotational world with the linear world. All right, so in this case, A would be equal to 3g over 2L, that's my alpha, times my R, but in this case, R is what value? Okay, but actually the R is the entire length, so that's just going to be L like that. Okay, so what happens to that equation? The L's cancel, so I get 3g over 2. Okay. What do you notice that's really strange about that?